This video is meant to be a continuation of a previous video on Lenz's Law. In particular, in this video, we'll look at a few more examples of how Lenz's Law works. So just to rehash, of course, the main statement of Lenz's Law is that Lenz's Law is about inducing a current that produces a B that opposes some change in an external B. So a lot of words in that sentence here. So the first thing is that about Lenz's Law is really about finding the direction of an induced current. And we know from previous work in the class here that currents produce magnetic fields. So if you induce a current, that induced current will produce its own B field. And the clue to getting the direction of that induced current is that the B field the induced current produces will always oppose some change in an external B that you might have going on. So there's really two magnetic fields going on. One is some external magnetic field, some external B, so something produced by your own magnet or some other magnetic source, or maybe you're moving the wire away from a magnet, but in either case some external B changes. And as soon as some external B starts to change, Lenz's Law will kick in and induce a current to try to oppose that change. So let's see if we can look at a few examples of that there. So the first one that we'll look at is something like this. Here's a system where a magnetic field is pointing straight out at us like that. That's what those dots mean. You should know that by now. And inside of this magnetic field region, we'll put a loop. So there's a loop like that. And remember, these black dots here are the magnetic field, and there's the loop right there. Okay? So what we'll do is we'll use Lenz's Law in a couple different ways. The first one is, what direction would the induced current be in this red coil here if the B, as it's shown here, so this is like part A of the problem here, if the B is shown in this problem here, B is increasing. So what that means is you see these arrows here, which is a magnetic field, but if you could visualize them somehow, these arrows here would be growing in strength. They'd be growing towards you. That's what it means that B is increasing, so these arrows are growing. So here's a loop here, and this B here, this black B that's growing, is like that external B that I referred to in the passage that opened this video up, the external B. So the external B is changing. It's getting larger. So what's the direction of the current going to be? Well, if these lines are getting larger right here, the induced current would really like to oppose that change. And the way you would oppose magnetic field lines that are growing towards you like this would be to induce a magnetic field which is into the plane of this whiteboard here, because that means a magnetic field which is growing upwards like this can be canceled by an induced one that goes down the other way like that. So we'd really like an induced magnetic field which is going to be down like that. So these little X's here, this is going to be the induced B field. It wants to be down like that. So then the question is, what current in the loop would be required to produce a downwards pointing magnetic field? Well, if I put my thumb in the direction of current around this loop and curl my hands into the loop, looks like down like that would work. So the answer to this problem here would be the current would be like that. B is increasing, and so I'd answer this by saying the current would be clockwise. I would be clockwise in this loop in order to oppose this change in magnetic field. Okay? So I'll try and do a bit of selective erasing here so I don't have to erase the whole scene now. So let's get rid of that induced magnetic field, get rid of this induced current direction right here, and we'll ask part B of the question right here. Say B is constant. That's the next question. So you're looking at a system here where there's these magnetic field lines, these black dots here again, pointing at us. There's a ring in the magnetic field region, but this magnetic field is not changing its magnitude at all. These arrows are neither growing nor receding, they're just sitting there like that. So if B is constant, well, then that change in external magnetic field, there is no change. So the induced current then is just going to be zero. There's going to be no current in this red loop if the magnetic field is not changing. Okay? The last one here says if B is decreasing. So what you're looking at here is you're looking at all these magnetic field lines. They are pointing at us, but they're getting smaller, they're getting weaker and weaker and weaker and weaker. They're sort of shrinking in size as they diminish like that. They're getting smaller. Okay, so there is a change in that external B. Lenz's Law is going to kick in. If these arrows are getting smaller, what Lenz's Law is going to do is getting smaller in this direction. Lenz's Law would really like to enhance them back, ask them to grow back again. So it's going to do some magnetic field which is up also. So I'm going to draw some dots like this and say, unlike the X's in part A, these arrows here, these are going to be the direction of my induced field. So the question is, what direction of current in this red loop would I need to grow these lines back or create an induced magnetic field which points at me also? The way it looks here, well, I put my thumb in the direction of current going around the loop like that, wrap around under the loop like that. It looks like my fingertips are pointing up in the right direction. So just the opposite of part A like that. The induced current is going to be this way. So the answer to this one right here is that I would be counterclockwise like that. That would be the direction of the induced current. So there's a Lenz's law example for it here, where B is in a particular direction, it's increasing, staying the same, or decreasing. And I'll leave it up to you, but sort of the equivalent problem would be then to replace all these black dots here that you saw in the original problem, replace them with X's, where the magnetic field is going into the page, and maybe work through it yourself here to say, what would the induced current be in this loop here if the magnetic field was increasing into the page, or constant, or decreasing into the page? I'll leave A and C up to you. B is easy. If the B is constant, there will be no induced current, no matter what direction the magnetic field is pointing. Okay? Next problem will look like this. Suppose we have a loop like this. Here's a loop, and the loop is connected to a switch that's connected to a battery like this. So there's a battery, it goes around like that. So there's the loop. And I'll try and put a bit of perspective on it like this. This thick edge here is the one that sort of points towards us like that. And now what I'll do is I'll draw another loop above this one. It looks like this. And once again, this thick edge is towards us here. So I have a couple loops like this. And hopefully the perspective works. Then actually, let me just draw an axis of these two things. So like the axis would come down like this and sort of get broken and come out of the bottom like this and get broken again and come down like that. That's sort of the perspective there. So hopefully you can convince you these thick edges are towards us here. Okay? So the question is, the loops aren't touching at all. But the question is now, if I close this switch, what direction is the induced current going to be in this upper loop? It's a pretty wild question because the loops aren't even connected or anything, but let's just look at what happens one at a time. Okay? Here we go. If this switch is closed here, this sort of in an abrupt sense becomes abruptly closed like that, what we get is this loop here goes from suddenly no current to maybe some maximal current. There's even a buildup in there, if you will, but then it'll reach some steady state. We'll talk about that in a second. So as I close this switch here, just keep in mind that the current in this loop here goes basically from 0 when the switch is open to some maximum number. And the delta T on that is going to be, let's just say, it's sort of fast. It'll happen pretty quickly, but there is a transition in there from 0 to max current. Okay? So when you close the switch like that, the current is going to travel in the loop around this direction here. And the reason why I know that is these conventional current flow, which is the way it's conventional to talk about it in physics, text, and engineering and so on, is that current, when it comes out of a battery, comes out of the positive terminal, goes around the circuit and back into the negative terminal like that. So this is going to be the direction of the current. Okay? So if this is the direction of the current, this loop here is going to create its own magnetic field. Let's see if we can figure out what that direction is going to be. So I put my thumb in the direction of the current as it goes around this lower loop, and I curl my hands back. Imagine going under the loop here, back up like this. There's going to be a magnetic field which is up because of this lower loop. So suddenly this magnetic field is going to be up like this, big B field like that. And I realize I'm sort of ruining the problem here, but you have to remember that the magnetic field line goes into the interior region of this upper loop here. So let me get that black line back and solid again like that. So that's sort of the situation that we're looking at here. So the magnetic field, because of this lower loop, because the switch is closed, is going up. And in terms of the increase or decrease, remember that we said that the current goes from 0 to some maximum, and we also know that the magnetic field, this green magnetic field, is sort of proportional to I. How do I know that? Well, it comes from either the magnetic field of a loop, which has an I in the top like that, or you can also think that B is, mu naught I over 2 pi R for a segment wire, something like that. But we just know, generally, for some of the systems we have, that the more current you have, the stronger magnetic field you're going to have. Okay? So what I know is that as I goes from 0 to some maximum number, the magnetic field, this green magnetic field, is also going to make a transition from not existing, being 0, to some maximum magnetic field. There'll be some ramp up. So in other words, this upper loop will see a changing magnetic field that goes from 0 to some maximum, and we're asking for the induced current during that buildup, that maximum. So what this loop is going to see is this magnetic field is going to grow up towards it. But Lenz's law would like to oppose that change. So the induced current in this upper loop here is going to be in a direction that's going to try to cancel out this upwards going vector. Or in other words, some induced current is going to be in a downwards direction like this. So let's just say like this, like this, like this. These are arrows pointing down like that. There's my induced magnetic field down. So the question is, what direction should the induced current be in this upper loop to make a magnetic field that's down? Well, if I put my thumb in the direction of a proposed current, I curl into the plane of the loop like that. That looks like down like that. So I'm going to get an induced current that's going to be in this direction right here. So the answer to this question is, when the switch is closed, there's going to be a clockwise induced current in this upper loop, and that's the way to fight that green magnetic field from building up. What happens when the switch is closed for a long time? Well, when the current reaches a maximum, which it will at some point, just start traveling around, it doesn't change anymore, there's no more growth in the current because the switch is closed, reaches some steady state, very short amount of time. Turns out B will become constant also. And so when this green magnetic field is no longer changing anymore, no longer building up, it becomes a constant. Lenz's law won't see a changing magnetic field in this loop anymore, so its induced current will disappear, it'll vanish. And this B field pointing down will vanish as well. So when the current is like that, the magnetic field will vanish because nothing's changing anymore. And so usually there can be a part B to a question like this. It's okay, let the switch be closed for a long time. What happens if we open it again? Well, what happens if we open it now is the current's going to go from its maximum value to its minimum value. It's going to be decreasing. Still going in this direction, but it's getting smaller and smaller and smaller. So what that means is these green lines here that this lower loop has produced, these green magnetic field lines, they're getting smaller and smaller and smaller as well. And Lenz's law will go, uh-oh, magnetic field is changing. They're getting smaller, but it's grown to like these green magnetic field lines, so it'd really like to build them back up again. So that means that if it's going to build these lines back up again, the induced magnetic field is going to point in this direction to try and build up those green lines, something like that. And if it's in that direction, this induced current can't possibly be in that direction like that. So what we have to do then is say, well, what direction would it be in? Well, if I put my thumb in the direction of this lower edge right here and curl my hands back away like that, can be up in the direction like that, and so the induced current is going to be in that direction like that. So when the switch opens up again like that, the induced current is no longer going to be clockwise, it's going to be counterclockwise like that to build that magnetic field back up again. There's another example of Lenz's law there. So let's look at one more example of Lenz's law. And this is also why it's important when you're doing these Lenz's law problems. Sometimes a bit of perspective is kind of important like this. So drawing neatly helps a lot. So here's a magnet here. Here's the North Pole and here's the South Pole. And what we have over here is we have a solenoid. Looks like this. And now what we'll do is we're going to draw the wires around the solenoid very carefully like this. So the one wire is going to come down like this. And it's going to sort of look like this. These wire ups almost look like integral signs from your calculus class. Something like this. And this last one over here goes back around the back of the solenoid and then back out like this. And you have something like an ammeter right here. Okay, so the question is following here. You have this magnet here, and you know the magnetic field lines come out of the North Pole. So if you started to shove this magnet towards the solenoid this way, the question is what would the direction be in this ammeter right here? So could you draw an arrow below this ammeter, either pointing to the left or right, to indicate what the direction of the induced current would be? So let's check it out. So the magnetic field lines, because of this magnet here, are going to point sort of in this direction like this. Of course, they loop back around to the South Pole, but that won't really concern us here. So as we move the magnet towards the solenoid like this, what happens? Well, in that interior, let me try and keep my perspective here. Let me get these lines back painted right here because these are on the outside, and those green magnetic field lines are meant to be sort of on the inside volume of the solenoid. There we go. So what will happen is the magnet is pushed towards the solenoid this way. This loop system here is going to see this increase in the magnetic field to the right, pardon me. As you push the magnet to the right towards the system here, these green magnetic field lines are going to increase towards the right in this volume of the solenoid here. That's maybe some common sense. You're bringing the magnet towards the solenoid. The magnetic field is going to increase in that same direction. So if that happens, the interior of the solenoid, according to Lenz's law, would very much like to oppose that change in the magnetic field. Does not want that change to happen. So in that interior region here, the solenoid is going to produce a magnetic field to try to cancel the buildup of that green magnetic field. So in other words, these blue arrows right here, these are going to be the induced B field. That's the induced magnetic field. Going to be towards the left. Okay. So if it's toward the left like that, then the question is, what direction of current must be in this system here to produce a magnetic field to the left? Well, you have to get your right-hand rule out again, and it looks like if I come down like this, my thumb is going to come down like this, and I wrap into the interior region of the solenoid like that, that's the wrong direction. My fingertips are to point to the right, wrong direction. But if I come up like this, come up this way, and wrap around this wire into the volume of the solenoid in that way, that produces a leftwards magnetic field. So I think I'd be right to say that the induced current in these wires is going to be up like that. So it's up through this one, It'll go down through the back, it'll go up through this side, down through the back, up through these sides. So it's going to just be upwards in all these wraps here. So here it comes, up in this wrap, down this way on that back wire, down this way as it comes out. So the current's going to be this way into the ammeter. And it'll just come back around and feed this wire up and go right back up again. That would be the direction of the induced current. So of course the next question would be, well, that's fine. Now what if we move the magnet up to a certain point, just hold it there and don't move it anymore? Well, if you don't move the magnet anymore, that there's no change in the magnetic field, so the induced current's going to drop to zero again because there's no change in magnetic field. Now if I pull the magnet back away again, what we're going to see is the B field still points to the right, but it's decreasing. Points to the right, but it's decreasing. Why is it decreasing? Because I'm pulling the magnet away. Why does it point to the right? Because the North Pole still points this way. So what will happen now is the induced magnetic field is no longer going to be to the left because these rightwards pointing magnetic field lines are decreasing. Lenz's law will kick in and say, no, we like these magnetic field lines. We'd like to build them back up again. So there's going to be an induced magnetic field in this case here, which is going to be this way. Here's your induced B field that way. So what direction of current would make an induced B field to the right? Well, just imagine once again your right-hand rule. If a current comes down on this segment of wire, down that way, I wrap my fingertips down in the direction of the volume of the solenoid like that, that'll produce, see my fingertips are pointing to the right, that'll produce a rightwards magnetic field. So the induced current isn't going to be up, it's going to be down like that, and it won't be this way in the ammeter, it'll be that way right there. So there you go like that. So the answer to the problem is really twofold. I guess we can say, okay, here's induced current. It's going to be to the left if the magnet moves right. That's one answer right there. And the induced current is going to be to the right if the magnet moves left. And of course, the left, right, the L and the R here refer exactly to the current. Right down here in this ammeter, that's where the left and the right would be. Okay, so that's the last example of Lenz's law.